This is Dr. Heck, Consequences of Accidents in Industry. I'm looking at the tutorial problems in your tutorial handbook 6.2 and 6.4. In exercise 6.2, you're given two streams that are flowing into a reactor, one stream that is flowing out. I've copied the information about the streams and the outlet here to this picture. Using the flow rate and the molar mass, you can calculate the flow rate in moles per second for each stream. And since in this reaction there's no change in the number of moles with reaction, we can also see in the third stream that this is equal to the sum of the molar flow rates of the first two streams. So 1 kilomole of Edux reacts to 1 kilomole of products. Edux here is referring to the reactants. Also assuming steady state in this problem, the mass is not consumed or generated, and so the total mass flow rate is also 2.7 kilograms per second. So what this question is asking is that you perform an energy balance. And so the basic energy balance here is that we have some energy coming in, some energy going out, and energy that is being consumed by the reaction. We know this because the sign on the heat of reaction is positive. So this is an endothermic reaction, energy is being consumed. And we also have Q, some amount of energy here, which is associated with the stirring. So mechanical efficiency 0.85, this energy from stirring is also ending up as heat. So if you want to calculate the energy going in, so with these inlet streams, you have the mass flow rate, the heat capacity. Here there's a problem in the tutorial handbook. These values are given in joules per kilogram, but if you look, heat capacity values are almost always given in joules per kilogram Kelvin. And this temperature difference is being taken between the reference temperature and the actual temperature. So there we have for stream 1. Here we have this for stream 2. And in general then, when we calculate the amount of energy coming in, we'll get a value of 240 kilowatts. Coming out, we take the outlet stream, so here 2.7 kilograms per second times 1800 joules per kilogram Kelvin, and again this temperature in is equal to temperature out. This temperature difference with respect to T naught, this gives us a value of 194.4 kilowatts. And at this point I'm not going to show you the rest of the solution because I think this problem is not properly formulated, so the way that the reaction enthalpy is implemented to get the answer I don't think makes sense. So in this problem, hopefully you're able to calculate, to sort of formulate an energy balance and think about it, but I would ignore the rest of this problem.